Welcome back. So we are going to now continue on the next part on views and indices. It's a practical part again, so that should be easier to follow again. So quick brush up. That's a table. Now you know how mathematically it's defined as a set of maps, or if you prefer strawberry, vanilla chocolate, list of map or bag of maps. So this is a table. This is a query. What does it do in terms of relational algebra, this query? Is it a projection, a selection, an aggregation? What is that? Anybody? Yes? It's a selection, exactly. That's a selection. It picks a few rows. So it's some of the rows that are picked. The way you see it's a selection is because it uses the where clause, right? So the where clause does a selection. Here we have, I just changed the selection predicate. So this is the papers by Albert Einstein. These are the papers by Marianne Mirzakhani. This is, what is it called, this one? That's not a selection, that's A. You're scaring me here. What is this? Yes? A projection, yes, exactly. We've seen that over weeks, right? So this is a projection that just selects, picks a few columns and outputs on a few columns, right? So that was the letter pi, that was the letter sigma. So the where clause is a selection. And here we have a projection because we put the columns we want in select. And here this is both, selection plus projection. This is a grouping query, so this is an aggregation, right? So here we just aggregate how many by Albert Einstein, how many by Marianne Mirzakhani, and how many by Alan Turing. And when we have this, remember we have the key, the grouping key in here that we always also put in the select. And the other attributes, we need to aggregate them if we want. So title in that case as a count, renaming the column and so on, right? So that's we've all seen a couple of weeks ago. So I'm assuming you're familiar with that. We can also order, of course, that switches automatically to list of map semantics, right? Because you need an order. So order by year. And you also remember limit and offset that paginates, right? It allows you to see some of the results. Very important for the exam. If you don't want to crash your notebook, it's a very good idea to add a limit to your queries. Can avoid the waiting times in the notebooks. All right. So who is comfortable at that point with this? Right, we've seen it, we've spent several weeks on that. So now I want to show you a few things. Here are 4 queries. Does anybody notice anything on these 4 queries? Maybe they have something in common. On Zoom, maybe? Do you notice something? This? It basically repeats the same subquery. It's called the subquery because it's a select from where that is inside the select from where. Remember the table in the table in a table, inception. So we have the exact same subquery, select star from publications where author equals Albert Einstein, and it repeats. That might be inconvenient to always repeat the same thing, right? And so this is why when we have a query like this, and we are going to use it a lot. So what we do is that we just create a view. We give it a name, basically. So we say create view publications by Einstein as, then you put it, and you see what I changed in here. We basically give it a name. And so what happens is that then, instead of writing every one of these 4 times the entire subquery, I can just use the name that I just gave to it, as if it were a table like any other table. For whom is that clear? Right? So I told you it would be a bit easier than the previous part, right? So we give it a name with create view, and then we can use it. This is called a view, right? So to query a view, you can just use its name, just like as if it were a table. By the way, you can create a view. If you don't like the column names, you can also change them, right? So in that case, we didn't change the column names, so it was just using the same column names. But you can also say, For example, here I'm projecting to title and year, and I want to call them T and Y, just for an example, right? And so that's just not only naming the view, but it's also renaming the columns, right? You probably can achieve the same thing using title as T and year as Y, by the way. But just so you know, you can change the names of the columns in this way. Okay. So what that tells us is that there's more kinds of relations than we knew before. Before, we knew that there were relations that were persisted on disks. These are the ones that you do with create table and you insert tuples in them, then you give them a name. So these are the tables that are persisted. Persisted means that it's durability in ACID, right? It's forever. You keep it on disk. And on the fly, that's what pops up in your Jupyter notebook when you press enter after writing a query. So these are on the fly. They are just creating just for the duration of your query and then again lost, right? So these are on the fly relations. And we had these two, and now we're adding a third way, which are the views to which you give a name that also are part of your SQL ecosystem. So how do they relate? So the persisted tables, they are named and persisted. They have a name and they are persisted to disk. On the fly, they don't have a name and they are also not persisted. They are printed on your screen in the notebook, but then that's it. Then it's forgotten again. The views, by default, the views have a name, but they are not persisted. When you create a view like that, it's not going to store it to disk or anything. It's just a shortcut. You're basically saying, like, whenever I use that name, this is what I mean. So whenever you use here publications by Einstein, it's automatically in the background doing this, right? So that's really just a shortcut that you're defining, right? So this is not persisted. It's only names, right? Who is with me? But materialized views also exist. A materialized view is when you don't just create the view, but you also ask PostgreSQL to take a snapshot, to take a picture of at that time, at the moment you build the view, it's going to create a copy of the entire view and store it on disk. And then when you query it, it's reading it from disk instead of recomputing it, right? So again, I repeat, the normal view is going to be computed every time, right? It's just computing the current state of the data, the query that you associated with the view. Materialized view, it's just reading it from disk because it made a copy on disk of the table in question. For whom is that clear? Right? Very good. So materialized views can be faster because in a materialized view, you just read it from disk and you don't have to execute it all over again, right? But there is a problem. Be careful with materialized views because a materialized view is frozen in time. If the data was modified later and new things were added, and you have a materialized view and you look at the view, you'll see it as it was 10 hours ago, right? So you have to be careful. The normal view will follow the data, but the materialized view will stay in the past. And you would need to refresh it or update it when you do that. So think of the materialized view as taking a picture and then it's frozen, while the view is really just a dynamic shortcuts that follows the data. Yes?
What persisted means? Is it meaning printed on the screen?
Mm-hmm. So persisted means that it's stored on disk and the disk is still here if you switch off the computer or if you have an electricity blackout, right? So this is what persisted means. It's stored on durable medium, like a hard drive, an SSD, the cloud. That's what it means. It's the D. Remember ACID, atomicity, consistency, isolation, durability. That's the D of ACID, durability. That's the persisted, right? And so what I'm saying is that the tables that we saw with create table and insert into, they are persisted. They are stored on disk. On the fly in the notebook, they are not stored on disk, right? If you write a query in your notebook and it prints on screen, but then the notebook crashes or something, then it's lost, right? You didn't save it to disk or anything, right? So this is the difference between the two. Does it answer the question, right? And so the materialized view is a view plus plus. It's basically a view that also takes a copy and puts it on disk. right? And then it makes it faster to query, but it doesn't follow the data and might be out of date if you took it too long ago. All right. Now, when you create a view, a natural question that comes is, can you update it? In the sense that you can update a table, right? You can update a table by adding rows, by modifying data, by deleting data. So what about a view? Could you modify a view? So the first question to ask when you say you want to update a view is, what does it mean to update a view, right? So what it means to update a view, imagine that now I try to insert into my view Albert Einstein foo 1920. That modifies my view. But wait, a view is supposed to be generated from the data, right? So how can I insert something in there? Well, in fact, you're not really inserting something into the view. What you're actually doing when you do that is that you insert something in the original data, the original table that the view was created from. So you basically add this Albert Einstein foo 1920 on the publications one, the one that is actually the original table. Do you agree that if I do this, then the view will make this appear? Do you agree with that? So basically, when I say we update a view, what it actually means is PostgreSQL looks at this and tries to figure out what it can do, whatever it takes, to modify somewhere in such a way that it's as if you had actually modified that, and then the view looks like this, right? It pretends to update the view. Actually, it finds a shortcut somewhere else to make it so, right? So that's what it means. Okay. Very good. So in some cases, you can do that. Yes, go ahead. So what you're saying is very important. We need the microphone because it's actually exactly an important point, exactly what we're coming at.
So if the view is a projection, then not the whole information. As you can still insert something bigger than actually the attributes of the view.
So let's look at that. Do I have an example here? Yes. So let's take that example, right? You say a view that projects. So here we project to title. And so now we ask, okay, can we update that view, for example, by inserting a title, right? And so if I understand what you're saying correctly, what you're saying is if we just try to update that view adding a title, if we wanted to add it to the original table, we would need to also add something in the other columns, right? That's what you're saying. And we don't know what to put in there. What happens is that if these other columns, they are nullable, meaning that you allow the null value, or they have a default value, then you could set it to null, right? If you try to add to the view, you could set them to null. And if they are declared as not null and they don't have a default value, then you just cannot update it. Then if you try to update the view, it's going to tell you, no, sorry, I can't do that. That's not updatable, right? Does it make sense? Right. So that's a very important point. It's not always possible to update the view.
But if you would insert in a view something which is from out author, not Albert Einstein, and a different author, so if you then again execute the view, it would not be displayed.
I'm not sure I understood exactly so you mean that you insert a title? Yes, I think I understand. So you're basically saying here that the titles you insert in the view would be automatically Albert Einstein.
Yes.
Right? And if you want to insert from another author, then you cannot do that. Like if you want to insert from Mariam Mirzakhani, you can't, because that would add a title. Then in the original view, it would put some default value and some null, and then it would not appear as Albert Einstein. That's what you're saying. Yeah, you're absolutely correct. This is why it's difficult, basically. You're absolutely correct. The only way you could update that view is if the system is smart enough to figure out that you need to add in publications the title and put Albert Einstein as the author, not null or not the default value, right? And basically, I think the current systems, they're not able to do that in a general way. So they would just tell you can't. That's not updatable because it doesn't know how to figure it out. Right. Does it make sense? Yeah. So this is the idea. Sometimes it works and sometimes it doesn't work, right? So this one, for example, is a more complex view that is joining with another table. That's too complicated. Like adding something to the join would have to propagate it to the other tables. By the way, does it remind you of the chase algorithm? And that's kind of the same thing, right? We are trying to look at the tuples that are in the join and see so that the projections are in the original tables. But anyway, in fact, all I'm saying here is it's complex. It's very complex. In fact, it's too complex. And for this reason, it doesn't even bother, right? If you create a view like that and you try to update it, it's just going to tell you, no, sorry, you can't update the view. That would be too complicated to figure it out. Maybe people figure it out in the coming years. There's new features and they become able to update more views, but maybe it's not the priority to develop that. Okay. So that was the projection. That also you would need to be smart enough to figure that you need to also add Albert Einstein to the title that you add and so on. So basically, there's a few conditions for the view to be updatable in PostgreSQL. You only need one table name in the from clause. You can't do Cartesian products or joins. That's already too complex. In the select clause, you really need all the attributes. You really need all the attributes except those that can be null or have a default value. And you can't use R itself in the where clause because that also complicates things. You don't need to understand the details of that because that can quickly get complex. So basically, in the very simple cases where it's easy to do, it's done. And as soon as it gets too complex, then PostgreSQL is just going to tell you, sorry, we can't update the view in this way. Okay, everybody with me? Yes, I see a question over here. Maybe if you have the microphone.
You told the view is persistent. Can you now delete this persistent?
Oh yes, I think so. When you have a materialized view, you can also delete it. You can also remove it. I think you can also refresh it. You can also say, please recompute it as a newly refreshed version. And you can, even the non-persisted view, you can remove them when you no longer need them. Right? So it's just like tables. You can create tables and delete tables. You can also create views and delete views, right? But deleting a view doesn't delete the original data, of course. It just removes the view. Yes?
We said that materialized views are persistent. Why would you then use them? Couldn't you just make a new table? Or like in which case would you use that? And wouldn't it just be easier to make a new table?
So critical thinking, that's very good. And indeed, you have to ask yourself when you want or do not want a materialized view. A materialized view is typically when the view is so big or so computing intensive that taking a snapshot, you avoid recomputing it every time. You could indeed consider creating a new table, and then you do insert into that new table, select from where, blah, 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 and then you move the data over there, right? So you can absolutely do this. Then it's not a view, it's a table, right? You just created it from the original data. But when you create a materialized view, it remembers how it was created. And so it's easier to hit refresh. If a week later or a month later you want to refresh it, then you can do that. If, on the contrary, you created a table, then you need to remember, the burden is on you to remember how you created it, and then to re-execute the same thing to recreate it, to make a new version. Does that make sense? Let me give another example that what it makes me think of. Who has ever used Excel or equivalent spreadsheet software to import CSV files in Excel? Right? Who remembers seeing that you can right-click and do refresh? when you do that, because it remembers that it comes from a CSV file. And so if you replace the CSV file with a new file, you click refresh, and it's automatically changing. That would be a materialized view, essentially. Persisting would mean that you forget the CSV file. You would basically go somewhere in Excel to say, okay, forget that it came from CSV, and now it's a full standalone spreadsheet that doesn't remember where it came from. That would be a little bit of the same idea. Right? Does it make sense?
Yeah, thank you.
So the materialized view is really a feature that remembers where it came from in such a way that you just need to push a button to refresh it. That's essentially what it gives you. Yeah. Okay. And of course, compared to a normal view, it's faster because when you need it, then it directly reads from the snapshots that it took. Okay. A question on Zoom, yes?
If you update the view, will the relation you modified stay modified, or does it lose the information again?
Indeed, if you update a view, it modifies the original relation. It modifies the original relation in such a way that the update of the view has the change you wish, but it does modify the original relation, yeah, and persists the change. Mm-hmm.
What is the difference between a table and a materialized view? A materialized view is for long and complicated tables, which we have to calculate repeatedly. Is this the difference?
Yes, exactly. That was basically similar to the question you asked. So indeed, when you have a materialized view, it remembers where it came from, and then you can easily refresh it. If you would copy over to a new table, then you would have to redo it manually and remember yourself how you did it. Yeah. It puts more burden on you, basically.
I also have a question about the view thing. What is the difference? Also, maybe someone else also wondered it with view and with clause, because with when you.
That's also a good question. So I would say that a with clause is like a view that only survives for the time of your query. So when you say with, you give also a name just like to a view, and then you can use it in your query. But once you have pressed return, then go to the next query, it's forgotten. It doesn't remember. So you could consider that the with clause is a very short-lived view, right? While the create view is the view that outlasts the query, that stays there for multiple queries. That's the difference, right? Also, I just remembered I add one more thing to the difference between a materialized view and a table, is that if you want to update the view and it propagates to the original table, if you create a table and update that table, then it will just update that table, but it's not going to propagate anything to the original data. That's also an important difference. So you see, it comes with a few bells and whistles and nice features. All right, so these are the views. Now let me transition to indices, showing you that it's related. What you need to understand for the views is that it's a gain in productivity and performance. It's a gain in productivity because instead of copying the entire subquery every time, you just use the name. So it's good for productivity. You're faster when you write your query. And it's good for performance because if you have a materialized view, then it's going to be much faster to execute because you just read from what you copied on disk for the materialized view. So productivity and performance. Indices are also there for performance. They make your query faster. Indices is the plural of what word? What is the singular of indices? Index, exactly. That's an index. Who remembers reading a technical book like O'Reilly or whatever, but actually I think a lot of books have that. And then at the end of the book, you have like 10 or 20 pages with an alphabetical list of words with the pages on which they are found. Whoever saw that? I assume everybody, right? These alphabetical lists at the end of the books. This is an index. This is an index. And these indices, they have existed for thousands of years. I don't know if you have actually experienced a non-digital library, because now when you borrow a book in the ETH library, you just give your leggy and it's scanned. But when I was a kid, I would go to the library and borrow a book. It wasn't like that. We didn't have the computers to do that. So what you had instead is that the librarian had a little box with sheets of paper, and there was typically a sheet of paper inside every book at the end that has the title of the book, and then they would write your name on this sheet of paper and then put the sheet of paper in their little box. And the box has somehow a sorting, an alphabetical sorting on your name. And so whenever you bring back the book, they look you up in that little box and pick the sheet and then put it back in the book and put it back on the shelf. And they would know if somebody is overdue, because since they have the sheets in their box, they can look at them, to see if any book is overdue. So this is in fact an index. It's an index on the books that were borrowed from the library, except that index is not in a computer, it's on paper, right? So people have been doing that for thousands of years. They just artificially did them with paper manually to make it work. So really think of an index as a few additional pages at the end of the book that allow you to look up very efficiently the pages where a certain concept is studied. Who agrees that it's faster than trying to read the entire book and find the words? Right, that's the idea of an index. So now, more concretely, let's do it on tables because you will see the same idea. Imagine that you have this query which selects Albert Einstein. In order to, it's not working. Yeah, there you go. So now what I'm asking is, how is this query computed? So you have a very large table and you want to do a selection on that table. Well, normally, the only way to do that is to have a full scan on the, I'm clicking too fast, or there's a delay when I click, sorry about that. So this is the original table. And in order to answer that query, you need to go row by row, one by one, and to ask, okay, is that Albert Einstein? Is that Albert Einstein? Is that Albert Einstein? Right? So it's like this. Okay, look at the first one. Is that Albert Einstein? Yes, that's Albert Einstein. Okay, let's look at the second one. Is that Albert Einstein? Yes, that's Albert Einstein. So I'm adding it to the results. The next one, no, it's Mariam Mirzakhani. That's not Albert Einstein. So that's not part of the results. The next one, is that Albert Einstein? Yes, that's Albert Einstein. The next one, is that Albert Einstein? No, that's Alan Turing. Next one, that's Albert Einstein. Yes, we add it. Albert Einstein, yes. Alan Turing, no. Here it's again Albert Einstein, we add it. Mariam Mirzakhani, not Albert Einstein. So we don't add it. And Albert Einstein. And now we are at the end. And so we can return these rows. Who agrees that this is how it can be done? Right? So this is a selection. Now you probably noticed it took me a while because I had to go row by row and ask, okay, is that? Now imagine if there were millions or billions or trillions of rows like that. That's going to take forever. And in fact, it takes forever. If you try to do this, you create a table that's very large and try to execute that query. It's not going to be instant. It's going to take a while. And in fact, that's exactly the sort of things that we want to accelerate. Because there's cases where it's extremely frustrating because here there was a lot with Albert Einstein. But what if I'm looking for one specific record? Not several of them, but just one. So let's look for the theory of relativity. Is that the theory of relativity? No. Is that the theory of relativity? No. Is that the theory of relativity? No. I could go on and on and on, like, yeah, no, that takes forever. No. Yes, we found it, right? But it took me forever because I just had to look at every single record that there was in the table. Right, now we found it. Can we do better than that? Yes, of course we can do better than that because that's the whole purpose of this lecture unit. So let me show you that table. Maybe you noticed something about that table, and I'm asking you, where's mathematical logic? Who found it? Okay. Who was able to somehow find it a bit faster than scanning the whole thing? And why? Yes? Okay, so I'm repeating what you said. So you're basically saying it's because it's higher up, right? What if I tell you it would also potentially be fast to find even if it were at the end? Did you notice anything about that table? The title is yes. So, but here it's because you're a human, right? So, so yes, absolutely. So you're a human, so you see that the string is shorter, so you immediately look for the short values. That's because you're a human. So that's a perfectly valid point. Maybe with AI that would work, but here we don't have any AI, so we have to do with more easy things. Yes. Yes, the titles. Go ahead. Yeah, so I'm repeating, you basically observe that the titles are alphabetically sorted, right? Also, as a human, you noticed, of course, the computer, we would need to tell them that it's alphabetically sorted. Why is that faster? What did you do? What does it allow you to do? Clever. So basically, you're saying, okay, based that it's the letter M, you visualize more or less where it's going to be, right? This is indeed one aspect, so you could argue that. Any other reason? Yes? Yes, that's also a valid point. So depending if it's at the start or the beginning of the alphabet, you could start the scan. You could start the scan from one side or the other. That's perfectly valid. Maybe I can ask also another question. Who thinks that I would be able? Imagine it's alphabetically sorted, and there's a million entries in the table. Can you find it without actually scanning everything? I see a raised hand over there. Absolutely. So you say divide and conquer. That's exactly the idea. So imagine, so here we find it because again, as a human, I see it immediately. But the reason it was fast is let's divide and conquer. So you split it in two. You look randomly in the middle. That's O. Is M before or after O? M is before O. So you already invalidate what's after that and look at the first half. And then you divide and conquer again. You divide it in two. You divide it in two. Do you notice that I didn't look at everything in there? I looked at less records than everything, right? So that's the spirit of divide and conquer. That's also called the binary search. In fact, do they still teach that in a primary school, how to look up words in a dictionary? Or maybe they stopped teaching it because we can just do it on a computer. When I was a kid, they would teach us, you know, you have this dictionary in your hand. You first start exactly in the way you said, meaning you know the letter and you know roughly where it is in the dictionary, so you open it. And then it's exactly the divide and conquer thing. You just look a bit further and then you divide in two until you find the word. That's the technique. Of course, now we are spoiled because we have a computer, so we just directly put in the computer what we are looking for. But in fact, the computer is still doing it in this way. We used to do it manually, but the computer is still using this divide and conquer to find this entry. And so what happens, in fact, is that this divide and conquer implicitly has a tree structure. You basically start in the middle, then you know you go to the left because M is before, so here it's D, so M is on the right, and so on. Do you notice that we only looked at 4 values in here? The ones that don't have a color, we didn't even touch them. We didn't even look at them. What's the complexity of that? For anybody who knows complexity theory in the size of the table? Yes? It's logarithmic. It means that if you have a table with every time you add a 0, it only adds a constant number of steps. Every time you have like 10 to 100, it's the same as 100 to thousands. It's not increasing exponentially with the table. It's just the logarithm, right? So that's called the logarithmic complexity. Of course, formally, it's not explained like that. I just try to give you an intuition of what it means, right? It's basically the logarithm, the number of items you have here, is roughly the logarithm of the total number of items in there. Okay, and so we're actually done for today, but next week I will just show you that you can actually, just by pressing a button with a simple command, PostgreSQL will create that for you, and then everything becomes magically faster. That's what's beautiful about having a system like that. So thank you very much, everybody, for attending today. Enjoy the exercise session. Thank you, Denise, for moderating, and I will see you next week at 10 a.m. for the continuation of this lecture. Thank you and goodbye.